Okay. Hello, thanks everyone. So today we're going to have a great discussion about black holes with our dear participants who are here presently and online. I think you will love it, and there will be some time for your questions at the end. So, Professor Paulo Crawford, the word is yours.
All right.
Thanks.
Well, I was invited to be here. I'm an old professor, and I was one of the first person in Portugal, particularly in Lisbon, that start working on this area. Well, what area I'm talking about? I'm talking about Einsteinian universe, if you put this very simple way, easy way. And indeed, in those times, let's say 1970, 98, in those times, very few people were studying this subjects, and I don't remember anybody in my department, physics department, in the Faculty of Sciences, that were interested in these problems of universe and all the things that his universe, the whole universe, started and everything related with that. But after a while, of a group of people that started in Lisbon, same happened in the north country, like in Porto, and much less in Coimbra as well, one or two, but mainly Lisbon, Porto, and then Coimbra. And some people came from some time, like this friend of mine this year, that was one of the first after the older ones, like me, and there is a professor here that worked with me, Pedro Mimoso. Maybe some of you are here might be in touch with him, and he's still teaching here. He's very close to the end of the work in here, but he's still working here and producing. And there are some other more, like Nelson Nunes and many other people. I'm talking about, I know that some people here don't belong to this university, this faculty, but maybe few of them might be from this university. And even if you are from other university, you might be in touch with these people. Although, of course, in your university, in your school, you probably have other people to work with. Although it was something only started, as I said, let's say after 1980. So you see, it's not so far away. No? So something like 40 years, let's say, about between 30 and 40 years. I was expected to be. You see.
Eu penso que não, nós temos o nosso microfone ligado, acho eu, mas a gente pode ligar.
Muito bom, não.
Is it working? Can you hear me?
Yeah.
Okay.
At least for me, it is working.
Okay, nice.
Okay.
Sorry.
But I'm not sure for Floor.
Okay. Then we will ask you to explain everything we are going to talking about.
Hey, here, now I have sound. Sorry.
Right.
Anyway. Well, going back, I think I don't want to be the person to speak more. I have to I want to be the one that is going to speak less, because there are younger people here, and we have to discuss with the people over there. I suggest a very important topic that many people is already talking about this. And the subject I was trying to propose for these discussions was about black holes and holes that has to do with black holes, how they form, how they evolve, where they are, like for instance in the center of our galaxy and in whole galaxies, as far as we know. In our galaxy, in the center of our galaxy, there are many actual black holes, not just 1, 2, or 3, or many, and some are very big. Actually, when they collide with each other, it's possibly that this would produce a bigger black hole, and mainly this is common, not just for our in our case. There is one person in particular that is a very good writer about these topics, that I suggest you. There are some books, even in Portuguese, recently. Maybe it's better you buy in English, because you never know if the translation is good enough. But the person I was suggesting for you to follow and to learn with him is Carlo Herdeiro. Carlo Herdeiro is an Italian guy that after a while studying in Italy, then he moved around first to France, then to the United States, and so on. And he's producing many books. Recently I have seen one of them already translated to Portuguese. I read all of them in English, but recently for people that has more difficulty with English, you can use this Portuguese. I don't know whether the translation is good enough, but it's a suggestion, a possible suggestion. And I think that this is one of the topics that we could discuss, all of us, with you. I mean, the formation of black holes, where they form, why they exist. Since then, they exist, the beginning universe or not. It was the Big Bang, an explosion with a black hole already, or only afterwards. Well, we have people, I in particular know very much well. This chap is next to me on my left. I don't know so much this lady. And I know about him that he is a very good physicist and a very good relativist. He knows a lot. So he's going to help me and help you to discuss about these topics, all right? And I should stop now and give the word for other people, and then you probably will have time for asking questions. Okay? You accept?
Thank you, Paulo. So hi, everyone. Hi to the audience and the colleagues in the panel. It's really a pleasure to be here. So my name is Carlos Herdeiro, and I work in strong gravity. So a little bit about me. I don't want to sound too egocentric, so I'll just give you a bit about my bio. So I'm from Porto, where I did my undergrad many years ago. Then I moved abroad, like many of us, because when I was a student, this community that we are very happy that we have in the country right now, it didn't exist with the same expression in those days. So because I wanted to study general relativity and generalizations thereof, I decided to go to the UK. I did my PhD in Cambridge. Then I moved to the US. I was at Stanford as a postdoc. And then I moved back to Portugal, first in Porto. Then I was hired by Aveiro, where they gave me the opportunity to start a group in this area, which I did. So right now we have a group of about 20 people, evenly split more or less between PhD students and researchers. And we focus mostly on compact objects. So by compact objects, people typically mean something like neutron stars and then black holes. But not only, well, we focus on black holes, both from a more mathematical viewpoint and as a means to test fundamental physics. In the meantime, I should say that I also came to this university where I worked for some time, but then I moved back to Aveiro. So our group, as I've said, essentially focus on trying to understand, in these very exciting times we live in, what are these astrophysical dark compact objects that we call black holes. So are they what we think they are? So in general relativity, it's offered a theoretical description of them in terms of a very simple, in a sense, elegant solution of the vacuum Einstein field equations, which is called the Kerr solution. So are these black holes really described by this theoretical solution of vacuum general relativity? And by vacuum, it means without sources, because when everything settles down, at the end of the day, it's as if no matter is around the black hole anymore. Of course, then there can be accretion disks and some very interesting dynamics. So testing this Kerr/black hole hypothesis is one of the central goals of the community at the moment. And we live in exciting times because after many decades in which these objects have been around, theoretically speaking, now we are starting to have some precision data. You've all heard about gravitational waves from colliding black holes. You've probably all heard about the images of M87 star, the giant black hole, supermassive black hole at the center of the M87 galaxy. Also the image about Sagittarius, a star, which is again a supermassive black hole, although not as supermassive as the other one, but it's much closer. It's at the center of our own Milky Way. So by having these sort of things, these images, and also some other evidence, for instance, the data from stars going around the Milky Way center, Sagittarius A star, which gave rise to actually a Nobel Prize of Physics 2020. We are starting to, have some probes about how space-time, how the gravitational field behaves in the vicinity of these black hole candidates. So we can test our theories. And this is really what we are interested about. But, we also kind of like to explore ideas. And that's one of the fun things about being a theoretical physicist or a mathematical physicist, is that you can explore ideas and use, the laws and the mathematics as kind of playgrounds. So you come up with new solutions which might differ from these ones, and you try to explore their phenomenology. Could they explain the data? Or are they incompatible? And again, the very important thing about the time that we live in is that not everything goes, because we have data. And so there are kind of constraints, because if you have another black hole, but the image, if you try to make it more or less realistic, would give something that is not compatible with what we see in the actual images of the Event Horizon Telescope collaboration, it doesn't go through. So I think that's enough for my first kind of, and then I'll pass it on. I don't know, Paulo, please, or Rita, I don't know.
You want to say anything?
Should I introduce myself or should someone else? Me?
Yeah,
Okay.
yes,
Okay. So hi everyone. Thank you to the organizers, to people from FACE for inviting me to talk here. So I'm the youngest person here. In this not on Zoom, but in the physically here panel, and I'm not yet a professor, so I'm a postdoc in Princeton. I was previously an undergraduate student here at Técnico, where I did Engenharia Física Tecnológica, like many people here are doing. And then I moved to Cambridge, like Carlos, to study general relativity. So in Cambridge, I did my master's and I did my PhD, and that's when I moved to Princeton to become a postdoc. And I'm going there tomorrow, in fact, for one more year before moving back to Cambridge to start a position as assistant professor. So not a professor yet, which means you can still, treat me like one of you guys. At least that's what I like to think. Okay, so that explains my bio. What do I work on? Well, I consider myself to be a mathematician. So as I said, I studied physics, but when I was here, I always enjoyed my math classes. And when I went to Cambridge, I veered more towards the pure mathematics side. So I like to think about general relativity as a mathematically well-posed theory, where essentially you have Einstein's equations, which are the backbone of the theory of general relativity, as hopefully you've heard in some lectures. And I like to think of them as a set of differential equations that where the unknown, so this is an equation where the unknown, instead of being instead of you looking for x equals 3, you look for G, where G is essentially a space-time. So that's you have a set of equations where the solution is the space-time in which we live. And of course, these equations are very complicated equations that typically we cannot solve analytically unless we have unless we are under very special conditions. So essentially, as a mathematician, but I think this is true for all of us, what we want to be able to do is we would like to be able to, even without knowing how to analytically solve these equations, analytically figuring out what is the space-time, we want to be able to say some things about the space-time. And there are some people that try to say things about the space-time by looking at the equations, putting them in a computer, and getting numerical data, numerical predictions. There are some people that try, okay, let me look at these equations, let me look at certain limits where I can do some approximations of these equations, and then they become treatable and I can actually solve them. And then I live in this other part, which is I try to not solve them at all, and still nevertheless be able to say some things about them. I try to prove theorems about these solutions without actually knowing how to write them down. So essentially, I don't know how to write them in terms of the functions that you know, cosine, sine, exponential, whatever, polynomials, but I still know, I might still be able to say that there is a solution with some particular properties. So for instance, one of the things that I'm very interested in, well, obviously, let me just say that wanting to prove theorems, it comes at a cost, and the cost is, unlike Carlos, that is worrying about whether the Einstein vacuum equations are actually the physical equations that we should apply to think about astrophysical black holes. For me, this astrophysics is too complicated. This having to think about matter and accretion disks is too complicated. So I essentially just think about solutions in the absence of matter. So, for instance, these particular solutions that Carlo mentioned, which are Kerr black holes, which are somehow, well, to date, I think they are the solutions that we use as the gold standard to when we think about astrophysical black holes, so far we think about them as being Kerr black holes, because unfortunately, maybe for Carlos, the Kerr hypothesis has held up pretty well.
So
far, exactly. Well, obviously it will be proven to be false because there is an accretion disk. So, but yeah, so far Kerr black holes are pretty much our idea of what an astrophysical black hole looks like. And just to give you an idea, what one of the things that I study is the properties of perturbations of these black holes. So if I take a Kerr black hole and I perturb it somehow, then I let this evolve, it will evolve under the Einstein vacuum equations. And unless the perturbation that I've imposed on the system is really special, I won't be able to tell you what does the space-time that I get after the perturbation evolves. I won't be able to write down what does it look like. I won't be able to write down the metric in terms of cosines and sines and whatever. But what I try to do is I try to still be able to say some things about this metric, this space-time that we get. For instance, even though you might not be able to write down what the metric looks like, you might be able to ask questions like, does the metric still resemble the metric of a Kerr black hole? Does the metric, does it eventually settle back down to being a Kerr black hole? Those are the types of questions that we try to answer, and that's all related to a big conjecture in the field, which is called the black hole stability conjecture. And maybe this is something that we'll talk about more. I don't know. I think this is a good time to give the microphone to someone else.
Okay, you said enough. Well, I don't know which topics in particular you would like to discuss with us, or you want us to explain about something that you don't understand but you would like to understand. Well, I start talking about black holes because black holes is something that we are very curious about black holes, and we realize that black holes are very common. There are many kinds of black holes. They can have just a symmetric symmetry, but also there are others that are not. Yeah.
I'm sorry to interrupt. We have to introduce also Diogo and Floor. They didn't introduce themselves.
Yeah, they should perhaps
Yes.
Oh yes.
have the word for a little bit, both of them.
Although she is just in front of me.
No problem.
Okay, it's your time then. Are you listening? Please, go ahead. Thank you.
I'm sorry. I can start. Yeah, hi everyone. Thank you so far for all the lovely introductions. So I am Floor Broekgaarden. I am originally from the Netherlands, so from Holland, but currently calling in from New York, where I'm a postdoc. I graduated recently from Harvard, and I'm also about to start like a professorship at Johns Hopkins University. So I'm in a very similar position where I'm like still a student now, but soon going to hire hopefully and train a lot of new researchers. My research mostly focuses on what I call gravitational wave paleontology. So similar how people use fossils to study dinosaurs, I actually use like fossils, in this case gravitational waves that are coming from black holes and neutron star merging, to understand how stars that form these black holes and this is important because these massive stars that form black holes, they actually are really important for many processes in our universe.
Yeah, that's good.
Such as like producing oxygen and other heavy elements, but also supernova explosions, forming black holes, and kind of all the crazy events that I think are going on. So yeah, I'll hand it over to Diogo.
Okay, so now on to the actual younger member of the panel. So I am actually still a student. I'm currently doing my PhD in Germany, the Max Planck for extraterrestrial physics. And to try to describe the research I do in very simple terms, I sip from the theories, so from the ideas of Carlos, for example, and I try to apply them to the data and see if they actually match with what we see. In my particular case, with the center of the galaxy, so that be the motion of the stars around the massive black hole, or the motion of things that are actually even closer in, so flares, what we call flares, so the accretion matter close to the black hole, and try to see if these signatures that we do see observationally can give us hints into new physics, into describing the universe, and if actually GR is actually right, and if black holes are actually the best solution that we have to describe these monsters that you see across the universe. So yeah.
Well, I don't know what to say.
There's a list of questions from them.
Where is this list?
Okay, here it is.
You have the.
I think I do, so we can look at it, and if you'd like to actually.
Oh yes, I remember that. Yes, you are right.
So for instance,
actually, I had.
If you'd like to, I mean, there's many questions and many interesting ones. So.
Okay.
But maybe some of the proponents are here, and they could ask the question. Yeah.
Yeah, the first one comes here is about a photograph of a black hole, the first photograph of a black hole. Why was it such a complicated thing to pull off? Indeed, we wait a lot before we were able to get, in my computer, I actually...
It's here.
Yes,
That's right.
yes,
M87
yes.
star.
This is the best one.
Yeah, that's true. That's right.
If you'd like, I could say a few words about this one, but
Yes, please.
Yeah.
Go ahead, because I don't have many things to say about it.
okay.
You know more than myself.
So probably you know that there's this collaboration called Event Horizon Telescope Collaboration, which is a team that managed to get the photos of these two supermassive black holes. First, the one at the center of this giant elliptic galaxy called M87. It's in the Virgo constellation, again, in the sky, it's more or less in that direction. And there's a black hole there that's kind of black hole candidate, if you'd like, that's been known or identified for a long time. In particular, there's a jet that's coming out of this galaxy that has been known for about 100 years. So this ends, the one at the center, the black hole candidate at the center of the Milky Way, called Sagittarius A star, which has also been identified since the 1970s. These were chosen to be the targets of the Event Horizon Telescope for a simple reason. These are the ones of the identified black hole candidates in the sky, all of them supermassive, that are the biggest in terms of angular size. So the region that we associate with the size of the black hole is the largest. Now, how large is that? It is extremely tiny. So the sun or the moon have an apparent, well, an angular size in the sky, which is about half a degree. You know that, half a degree, about 30 seconds, arc second. So planets like, say, Jupiter, it has a little disk. You think, I mean, if you identify Jupiter in the sky, it's a little disk. You can see it very well with binoculars. That's a disk. It's not point-like like the stars. Mm-hmm. And it's a few tens of arc seconds. The size of these black hole candidates, the event horizon size, so the trapped region, the angular size in the sky is of the order of tens of micro arc seconds. So that's 1,000,000 times smaller than the angular size of the planet Jupiter. So you want to resolve this scale. That's very, very difficult. So in optics, and this is a basic law for observations, there is a law which says when you want to resolve a certain scale, you have to have a larger opening of your telescope. And then there's a relation, and that depends on the wavelength that you're using. So in order to resolve these very tiny scales and see, potentially, that there is something black there, maybe surrounded by something that's luminous, you'd have to have a kind of an opening, which is more or less of the size of the Earth. So you'd have to have a telescope which is of the size of the Earth. And that doesn't work. So what these people envisaged and actually put in practice is a network of radio telescopes, because they were observing in a particular wavelength, which is about 1.3 millimeters, because at this particular wavelength, you have that the environment around these black holes is transparent. And so you could see what's at the very core, say, of M87. So they were looking with this particular, and they had this network of several radio telescopes that were working as one, collecting data simultaneously. But in a sense, you see, this is a little bit like you would have a very large telescope, but only you're capturing light just in small, kind of tiny pieces of this very large telescope. So there will be a kind of, if you'd like, your image is not going to be perfect. And because of that, you have an image which is kind of blurred in a sense. So the challenge, the observational challenge, comes essentially from this. for instance, the idea about these sort of observations is to go, say, to space, to put extra observatories in space or on the moon, because that would increase this so-called baseline, that is the opening of these telescopes. So this is one of the problems. In the two observations that were successfully done, there is an extra problem for one of the cases. So M87 star is very, very large. So the estimated mass is 6 times 10 to the 9 solar masses. That's the 6 billion, the American billion, solar masses. The mass, which is estimated for Sagittarius A star, is 4 million solar masses. That's 4 times 10 to the 6. The other one is 6 times 10 to the 9. So the one at the center of our galaxy is 1,000 times less in mass. That means the following. So when you do an observation, you're actually looking at this for an interval of time. It's like a long exposure photograph. If your target is moving during a long exposure photograph, what happens? You see, like, it kind of gets blurred, goes around. So because M87 star is very, very large, you see time scale in which things happen, in which things change, due to causality essentially, is of the order of days, because it's such a large object. And days is also the exposure time of these photographs. The campaign of observation was done for both of them, actually, in 2017, and the results for M87 star were released in 2019, whereas the ones for Sagittarius A star only 2 years afterwards. Because for M87 star, they looked in this long exposure and everything was kind of still during this long, so you could essentially, you didn't need to average anything. The photograph was essentially not blurred by motion of what the environment around the black hole. But in the case of Sagittarius A star, it's 1,000 times smaller, and the time scale in which things happen is of the order of seconds or minutes. So in the few days that they were looking at it, the environment was changing constantly. And therefore, in order to get an image, there was some kind of averaging that had to be done. And this is something subtle. So that was a second challenge that had to be done for the smallest black hole, which nonetheless is really huge. So the fact that this is very, very tiny, the fact that you have therefore to use, this network of telescopes, and in the case of Sagittarius A star, the fact that you're looking at something that's varying in time in a shorter scale than your observation scale made this very challenging. And these are some of the reasons, and not the only ones, why this was a very challenging observation.
Thank you very much for your explanation. So, any more questions or want to say something about what was?
Why don't we take pictures of our own giant black hole in our galaxy?
That's the one. The Sagittarius A star is the one at the center of the Milky Way. So you see, because the one in M87, this is M87. This is 1,000 times bigger, but it's about 1,000 times further away. And that's the reason why their angular size in the sky is more or less the same. And the two of them, of the kind of catalog, let's say, of the black holes that we think we know, supermassive black holes identified for several reasons in the center of several galaxies, these ones are the ones that are largest in terms of their angular size in the sky. And that's the one why they were chosen for this observation.
Right? Any more questions?
I think we can't hear the Zoom.
We can hear the people on Zoom?
Yes.
Oh.
Yeah, you're with.
Maybe.
Yeah, we're speaking and we're not hearing you.
Maybe this.
Because, yeah, when we change the sound to here, yeah.
This is. Oh my god.
Well, can you see? It's not clear.
não estar aqui o som.
Diogo, I don't think we can hear you.
Yeah.
You seem very excited, but we can't.
Sorry, Floor, can you try speaking, please?
No. Okay. This is turn.
Podem tentar entrar e voltar. Aquilo está mesmo ligado.
Certo, mas se calhar pode. Se tiver uma coisa.
Can you speak now?
Yeah, can you hear me?
Yes, from the top.
Okay.
Just a second. Can you speak again?
Can you hear me now?
Okay, yes.
Okay, perfect.
Oh, okay. So I think I can get my excitement back. I was just trying to add to what Carlos was saying, of just to get a sense of the scale of this thing. Looking at both M87 and Sagittarius A, that on sky have the same size, it would be equivalent to take a picture of an orange on the surface of the moon. So it's something extremely small. And I mean, as Carlos was saying, it was a worldwide effort to coordinate all these telescopes across the globe to get this picture. If I may say one fun fact about the observations of both M87 and Sagittarius A star, is that because you have these radio telescopes spread across the globe, and each one of them gathers so much data that they literally had to fly all of the data on hard drives to both of the analysis centers, so one in Europe and one in the States. They had to fly the actual hard drives because they couldn't send it over WhatsApp. Well, I don't think they would send it through WhatsApp, but they couldn't send it through the web. So just to add to the human scale of this endeavor, that it's also another amazing thing that we can get this data and test these new theories of gravity, or even test the one that we already have.
So for the ones that are interested, actually there's a documentary in Netflix about the making of this image. And it's kind of, it takes you through the adventure. It also, there's kind of a parallel adventure, which is more on the theoretical side about understanding black holes. I don't know if you guys have seen it, but and at the end, there's a very, I find it really remarkable, which is a very nice image of a mosaic of the front page of newspapers from all over the world. Because when the image was released of M87 star, that was in April 2019, it caught the attention of the whole world, and a huge number of reference newspapers just had that on the front page. So you can see newspapers from all over the world, and then including, say, Público from Portugal, and the image is there, and that's great.
Any more questions? Comments?
So maybe I can add something else as well. And this of course is pulling the conversation a bit to my research. So while this picture of Sagittarius A and M87 are done on the millimeter wavelength, so it's radio telescopes. And as Carlos was saying, we have that problem of looking at the galactic center. Things are moving extremely fast on the time scales of minutes and tens of minutes. So whenever we do a radio observation, all of this gets blurred out and we get the average features of such thing. And in my research specifically, we work on a different wavelength. So we work with infrared radiation, where we don't have this problem. Of course, we cannot take a picture of the black hole, but we can still resolve things on the same spatial scale, and we can actually resolve them in time as well. So although you cannot get a picture, you can see how things are moving close to these objects. And just to give you an example, you can start to see, so the orange thing that you see around the picture, so what we think it's the accretion disk, so the matter that's surrounding the black hole and accreting to it, you can actually resolve it and how it actually is moving. So you see that it goes, for example, around the black hole in around 1 hour, something like that. So we're talking on timescales that are way shorter than what we usually associate with astrophysical timescales. And if one goes even further, so moving to yet a completely different detection method, we can go to something that actually connects with Floor's research, so gravitational waves, which is not light, but it gives us an insight into, it's another insight into how black holes work.
But Diogo, I think we had another question. Maybe it was for you. Do you want to say what your question was?
I cannot hear it.
We'll repeat it. Yeah, for you.
Okay, thanks.
Oh, the documentary Netflix. What's the title of it? I don't know, but if you put black hole, I think. Well, if you just Google it, you'll find it immediately.
It's something inspirational.
I think it's easy to find. Yeah.
I would like watch black holes, the edge of all we know.
Oh yes, that's it.
Yeah.
Okay.
Why does the accretion disk curve around when we see it's off curve? Yes.
You mean?
Yes.
Okay.
You want to know why it has that shape?
Yes.
Okay. So I'm happy to reply, but someone else wants to say something.
No, please go. You do that.
So not, first of all, I mean, accretion, the environment around astrophysical black holes is complicated. It's not necessarily the case that, the environment is a kind of nice and dormant type of accretion disk, like you imagine in Interstellar, if you've seen the movie. Well, especially having that color, which was inspired by the color of the solar photosphere to look familiar. But not only accretion disks have various shapes. It might be flatter, but they might be thicker. But they vary in time as well. So it's a complicated environment. So what's done to obtain the synthetic images to compare with these observations are mathematical, numerical simulations in a computer using general relativistic magnetohydrodynamics. So people put on top of the solution of general relativity that we think describes a black hole, they put a kind of plasma. And they put the best knowledge we have about how these plasma equations behave on a curved space-time. They let them evolve. They have to assign some sort of emissivity. This is the light source. And then there are complicated techniques called ray tracing and radiative transfer to tell us if there is an emission with some luminosity at some point, how does an observer sees that? And so they put this in the computer, and the conclusion is that in a kind of complicated environment, there is a resonance effect that is related to the existence of a particular very special orbit around a black hole, which is called the light ring. So black holes, they bend light. Like, you know, we've learned that in general relativity, one of the initial tests was the fact that they looked at stars near the sun during a solar eclipse, and they saw the stars where they shouldn't be, and that's because light is bent by the gravitational field. In the vicinity of a black hole, light is bent in a dramatic way, such that it actually becomes a closed orbit around the black hole. This is called a light ring orbit, and it's very, very special. For it can go one way or it can go the other way. For a rotating black hole, it's actually something that they have different radius depending if they go with the black hole or against the black hole. So the simulations show that there's a kind of enhancement, if you'd like, of emissivity in the vicinity of this orbit, because there's a kind of resonance effect. So you see, you can have the plasma sending you photons directly, and you see some kind of intensity, but some are actually shot in other ways, and they just go around once or twice. They are trapped there, and if they come to you, there can be a bunch of them coming from that place. So there's a resonance. So that kind of thing you are seeing is thought, although it's debated in the literature, to be a manifestation of this resonance that appears due to the emissivity and because of the special orbit. Okay? And this is very important. Why? Because this special orbit is a signature of the type of black hole. So, if it is indeed a curved black hole, or something else that is from modified gravity, something beyond general relativity, you would expect this orbit to be at a slightly different location. So if you would be able to measure the kind of the dark area and very accurately where this kind of bright emission ring is, then in principle you could test if that's a good model. What happens is that if you look at the synthetic images, they have a very sharp kind of thin structure which corresponds to this emission ring. But because of the blurring, due to our lack of knowledge of the image, because we only have a few telescopes, and so the baseline is not fully swept by observations, then it becomes blurred. So that blur thing should actually be something much thinner if we had a much better resolution. So you see, that what you're seeing is not a direct image of the accretion disk. It is thought to be a sort of a resonance effect. But it's because of this astrophysical environment about the black hole, which is typically something more complicated than a nice little accretion disk, just smooth, going around, very flat, and there's a lot of different accretion disks. So, I mean, I just wanted to say that things can be complicated, and people do the best they can, but maybe, the best we can now, actually, in a few years will be, thought to be not good enough. So there's, there's an evolution here.
Maybe just, oh, sorry, go ahead.
No, I was going to ask you, if in all this you were talking about, you didn't talk about the difference between rotating black holes and black holes that are not rotating. Did you?
Well, I just mentioned that these light rings, for the current case, you have the co-rotating and the counter-rotating, and they have a slightly different radius.
And then some ones might not rotate.
Yeah, that's right. But they still have these light rings. So a Schwarzschild black hole has this sort of orbit. So.
All right.
But
Okay, I was going to add just something very basic, which is, you have to keep in mind in this discussion that you're not actually seeing the matter itself. You're not looking at the accretion disk. You're seeing the light that the accretion disk emits. So that's why all of this applies. That's why, if you run a simulation, what you see is the light, and the light will suffer from this effect. You'll see, if you run a simulation, you'll see a very sharp photon ring. Then when you take into account all of the processes to actually take the picture, so when they run all of that, when they put the noise back in, then they get something that looks like this.
one extra feature, if I can just pick up. So you see, this particular black hole, we believe it's spinning because of this jet. The jet has been known since the early 20th century, actually. And the jet turns out to have a direction which is at an angle of 17 degrees with the line of sight. So the line of sight with M87 star, and the jet is slightly tilted. So it is thought, but it's not guaranteed, that this jet is going along the kind of polar direction. If that's the case, that would mean that this black hole has a spin which is 17 degrees or thereabouts tilted with respect to the perpendicular to this sheet. So it's rotating, therefore, something like this. And it's rotating in a way like this, such that this part is coming slightly towards us, and that part is going slightly towards the background. And therefore, that's the reason why you see a higher luminosity here as well, is a kind of Doppler shift, okay? So this is consistent with the picture of the jet. I should say also that the observations, unfortunately, at this moment are not good enough to distinguish just from the size of this black region, that some people call the shadow of the black hole, if this is a rotating black hole or not. But because of the existence of the jet, is thought that this is a rotating black hole. And by the way, the mechanism for generating these jets, which many people think it's because of the energy of the rotation, is something under debate. So there's a lot of things under debate, and there's a lot of questions. This is very complicated. And so whenever you hear something about this field, you should take it with a grain of salt and think, okay, this is something that people are still kind of thinking about. So not everything is settled, for sure.
Yeah, let me ask you something, maybe you could explain for us. We talk about alpha radiation from a black hole. However, in principle, nothing can get out of a black hole. Okay, can you put this together and explain why there is an alpha radiation?
This is the second thread of that movie, right?
That's right, exactly. And Andy and Malcolm kind of going about discussing these sort of things. Well, I don't really want to monopolize the discussion, so I think that you may. But I'm happy to say a few words about that.
Because I know that you are the best
to
explain these things here. I'm sorry.
No, so just a few words, because maybe. But one of the key questions is to understand how general relativity, in general, kind of finds a quantum, a microscopic description. And so black holes being, in a sense, the atoms of general relativity, the most basic object composed solely of space and time. This sounds kind of poetic, but it is in a sense true, and therefore it's very interesting. There are reasons to believe they have a microscopic description. And there's several evidence for that. And when you try to put, with some approximation, the laws of quantum mechanics, quantum field theory, actually, on a curved spacetime, to study a black hole, you find Hawking radiation. That's what Hawking did. And there was an idea that black holes had an entropy, which is the area that always grows. If they have an entropy, they should have a temperature. And so this kind of settled down in the 1970s, and it was revolutionary for our understanding of black holes. So it sounds like a paradox, though, that the black hole seen classically as something that is all absorbing. Now, all of a sudden, you have a radiation coming out from it. So there's many ways to try to understand that. I'll just give you one very simple. So the point is that the horizon, the virtual boundary of a black hole, is what we call a null surface, which means a one-way membrane. Things classically can only go inside. And being null means that it's tangent to the light cone. So the light cone, let's imagine that this is the outside, this is the inside. So if you are inside, you can only go more inside. A poetic way of saying it is that inside a black hole, the future is inwards, which is partly, it's kind of true. So, but quantum mechanics tells you that this light cone fluctuates. So it's kind of like starts to, have, because of the Heisenberg principle. So somehow there is a possibility that it could leak slightly. This is a very pictorial view of how quantum mechanics could allow a little bit of leaking from a black hole. But there's other ways, but I will not go more into that. I think this is probably enough at the moment.
I wonder if we could also give an explanation taking into account that if you have a pair of particles and the antiparticle, right, that are very close to the surface of the black hole, and if one of the particles get inside the other one, began a particle by itself, and can be seen as being a production of something that is that the black hole has thrown out, but actually it didn't throw; it was already outside. You know that I don't know if you could follow me. I mean, two particles, particle and antiparticle, very close to the surface of the black hole. One goes in, and the other one becomes a real particle, not a pair, not part of a pair, right? This is one explanation that is possible to understand why, although nothing can get out from the surface of the black hole, however, our particles coming as were coming from the black hole, from inside the black hole.
Maybe just around the topic to get like the better view, maybe of what Rita does. How can your work maybe try to predict some of the stuff we can see on the images or the data from the image? Because you talk about you getting theorems and predictions about how black holes evolve in certain conditions, sometimes some of the angle. So how can you, in your work, predict some of this stuff in order to understand if your theory is correct or not?
Well, okay, sadly, I can't yet, because getting this image actually, actually for people to check whether this image makes any sense, they don't need to know anything about general relativity almost. Because as Carlos said, what they do when they simulate things in order to see whether this image makes sense, whether it's consistent with general relativity, really it's just a consistency check. You simulate, and then you compare, and you're like, oh yeah, looks about the same. So the simulation is done, you assume that you have a curved background geometry, it's completely fixed, and then you superimpose on top of that, so you have this strange curved geometry, and then you put here a plasma. But you don't allow the plasma to change the geometry. So that's not very, if you wanted to think about the actual realistic scenario, the plasma will change the geometry because the plasma has more matter, and matter is supposed to change the geometry. But essentially, the effect is so small because the plasma is so little matter that it's perfectly safe, according to astrophysicists. I'm not one, so but that's what they tell me. It's perfectly safe to disregard this and just evolve the plasma on a fixed background. So that means that in order to actually get this image, you don't need to know how does general relativity predict the existence of a curved black hole in the first place. What you need to know is plasma physics, a lot of it. So I can't say anything about this picture, but essentially what I'm in the business of doing is just making predictions about vacuum general relativity. So I am really, in the scientific method, there's a part about, okay, you have a theory, you make predictions based on this theory, and then there's a part where you take data and then you compare it to the theory, and then you check whether the theory is correct or whether the theory matches the data or not. If it doesn't, then you throw away your theory and you start with a new theory. So for me, the role of mathematical relativists is to make sure that you have predicted that the predictions that you extract from your theory are completely rigorous. Because if you make any kind of approximation in going from theory to prediction, and then you go through this process and you find out that the data doesn't match the prediction, how can you be sure that the problem is with the theory and not with your approximations? You can't. So the business of mathematical relativists, that's the point of proving theorems, is you know for sure that you haven't introduced any approximations, and so you know for sure that if the data doesn't match, that means that the model is wrong. So, okay, the downside is we can essentially only handle somewhat simple theory. So far we can really only handle vacuum relativity. We can study vacuum black holes. We can study Kerr black holes, which are, comparatively speaking, really, really simple. But the upside is we get complete results. I mean, we are able to say definitively this happens, and it doesn't happen in some approximation or some limit. We know for sure that this happens. And sometimes in the process of obtaining these rigorous results, you can actually find new things. Because one of the problems with approximations, and let's say, for instance, me, I was a physics student. One of the problems that I had with being a physics student is you're often very guided by the data. And you shouldn't be guided by the data in the step of going from model to prediction. You want that step to be completely blind to the data. Because you want to, you don't want to introduce any bias in doing this. And the problem is when you do approximations, I often had this problem. I was doing exercise. I already knew what the answer should be. So I was choosing the approximation that would give me that answer, right? And okay, if you are proving theorems, then you can't do that. You just have to, every step has to be completely rigorous. And so in the process, you might discover new effects that you wouldn't have discovered if you had your eye set on a particular goal. There's also the tools that somehow, I think, when you try very hard to do approximations, you are constrained. So for instance, I said, one of the things that I work on is stability problems. I try to answer the question of, if I have a black hole and if I have a specific space-time and I perturb it, what's going to happen? I don't want to necessarily tell you how exactly, point by point, what does the new space-time look like, whether it's this or that, but I want to be able to say something qualitative about it, like, does it remain close to something that I know? Does it change drastically comparing to the initial point? Okay, and this is the type of thing that if you are trying to analyze with approximations, if you believe that the answer is going to be nothing is going to change drastically, then what you might try to do is, well, I'm going to assume that the perturbation is small. And so if the perturbation is small, I can use these perturbative methods where I say, well, if x is a number which is smaller than 1, then x squared is even smaller. And so I can throw away all of the x squared terms, for instance, right? And this is fine if at the end of the day you manage to, your initial guess was correct somehow, that the perturbations remain small. But suppose, for instance, I think one of the things where mathematics has the upper hand is when you actually want to prove the opposite. Suppose that you think that you have a particular spacetime that when you perturb it, it will change drastically. And this is an example of a spacetime like this is called anti-de Sitter space. This is a space that we think is unstable. This is a solution to the Einstein vacuum equations with a cosmological constant that has the opposite sign to what we measure in real life. It seems a little strange. Why would we look at this kind of spacetime? But, well, I'm not the best person to talk about why, but there are definitely people in high-energy physics that think that this spacetime is a good toy ground, playing ground to think about things like if you've heard the words ADS-CFT conjecture correspondence, this is the ADS there. So this is spacetime that we believe, when perturbed, you end up having something completely different. Namely, this is spacetime that doesn't have a black hole, and when we perturb it, we believe that, for a generic perturbation, we will form a black hole. Okay, and if you try to analyze this by saying, well, I'm going to assume that perturbations are small, I'm going to throw away all of, I'm going to throw away all the x squared terms, and then you get as a result that the perturbations are large. Well, there's a problem there. There's an inconsistency. Assume that the perturbations are small. You've thrown away a bunch of things. Then you get that the perturbations are large. And now you want to declare victory. So I think one of the nice things about mathematics is it gives you different tools that bypass this. You have other techniques that you can use in order to study these kinds of things. And you don't have to just. I think maybe one of the things that as physicists we can sometimes be constrained by is we want to be able to solve things analytically. We want to be able to say this is a cosine, And when you take modern mathematics, you can abandon this a little bit. Even if you don't know whether it's a cosine, you might still be able to say, well, I don't know if it's a cosine, but I know it's always between -1 and 1, and that's good enough for me. So I don't know if that answers your question, but yeah.
You've been talking about curve model. I don't know what is it, but can you explain it?
Yeah. So it's a solution of the Einstein vacuum equations, meaning it's a space-time. It's a metric, and it tells you, okay, this is how things curve, and this is a particular space-time that contains a black hole region. So a black hole region is exactly what Carlos was saying. It's something where once you're inside that region, you cannot come out. Okay, so this is just the space-time that that essentially it's a space-time. It's an idealization where the only thing you have in that universe is a black hole, and that black hole is characterized by two numbers, a mass and an angular momentum. And now you might think vacuum but mass. That's a little strange, and it is. I think when we say the word mass, you shouldn't really interpret it as mass in the sense that you or I have mass. You can interpret it more as an energy of this curved configuration. Okay.
But is it a hypothesis or?
So this is a particular solution. I think the hypothesis that Carlos was discussing is this solution. It's essentially the it's not just a solution that we like, and we like to call it Kerr. It's actually thought to be the only solution in 4 dimensions containing a black hole, which is stationary, meaning it's like a steady state. And the Kerr hypothesis, I guess, it's the hypothesis that this particular space-time is a good model for the black holes that we see astrophysically. And that's not obvious that this should be the case, especially because this is, an empty vacuum universe that only contains a black hole. Our universe is neither empty nor does it only contain a black hole. So, on those two, just by those 2 reasons, you should never expect that this is.
If I may just add a little bit on that, it's something kind of special that makes black holes special objects. Just imagine that you have a star, and or let's start with something simpler. So this object has a certain mass. I could have another glass, or I can put enough water in this bottle such that it has exactly the same mass as this glass. Would you agree? I could put exactly the same mass. Their gravitational field is quite different. Why? They have a different geometry. So you could try to do an expansion in multiples. So we have a technique to actually do. It's a different gravitational field. The same happens for stars. You see, if you have a star with a certain mass, and let's imagine that it has a certain angular momentum, a certain total rotation, and you have a different star with the exact same mass and the exact same amount of total rotation. Nonetheless, they can be different. Why? Because the currents of mass that give rise to the angular momentum and the distribution of mass is different. But then if you go into something that collapses into a black hole, then if it has a certain mass and a certain angular momentum, if all the matter has either dissipated away or fallen into the black hole, then these 2 black holes are exactly the same. And this is remarkable. So black holes only have 2 macroscopic degrees of freedom after this equilibrium has been reached. This is remarkable. In a sense, that's why you think about black holes as some kind of atom. You see, the fact that all atoms are equal. So you'd say, all electrons are exactly the same, right? This sounds like a property of the microscopic world rather than of the macroscopic world. That's number 1. There's this huge simplicity. And then there's another striking fact, if I'm allowed to say, which is the following. So we have evidence of black holes that go from a few solar masses, from about 5 solar masses. This is from kind of X-ray observations that date back to the 60s, 70s, and so on. And now we have evidence for solar mass black holes, like M87 star, that go almost to 10 to the 10 solar masses. So we are talking a few solar masses to 10 to the 10. That's 10 orders of magnitude. And the idea that all of these are described by the very same solution of the Einstein field equations called the Kerr solution, which has only 2 macroscopic degrees of freedom, how much mass it has and how much spin it has, spin into classical terms, that is angular momentum. And it's just that they are rescaled, but they are the same object, is something astonishing in terms of simplicity and power, if it's true. So it's like, you have like a football and the atom, because we're talking about 10 orders of magnitude here in scale, would be, the same object just rescaled. And that's not true, certainly for a football and an atom. But here in the macroscopic world, we have this object that seems to describe all these observations and that has a huge simplicity. So as a community, we should be skeptical about this and see and try to, kind of nail it down as much as we can. And one of the wonderful things about black holes is that they kind of bring together all these different disciplines. And we haven't heard a lot, but I think we should, about, for instance, other observations like gravitational waves. But you see, you have mathematicians like Rita, you have observational astrophysicists that maybe, are looking at accretion disks. You have people doing all sorts of numerical computations to simulate accretion disks, to make these black holes dance around each other, to see the gravitational waves they emit. You have the people that try to solve the equations using a variety of methods. So the black hole is like a hub that brings a lot of science together. There's actually people doing experiments in so-called analog models, in which they create analogs of black holes using fluids or using condensed matter systems to try to test, say, Hawking radiation. And this is, so there is this formula in the black hole temperature, which is the temperature of black hole has a certain dependence on the mass for the simplest black hole. And there you have the gravitational constant, G. You have C, the speed of light. You have h bar, Planck's constant, the reduced Planck's constant, and you have k, Boltzmann's constant. So you have the 4 fundamental constants in the same formula. So this is gravity, it's relativistic, it's quantum, and there's thermodynamics in it. So the black hole is this thing bringing all of the physics and beyond, a lot of science together. And therefore it's really fascinating, but it's extremely challenging. And so that's why I think it's so attractive, not only because of the mystery, it encompasses what is beyond, say, the horizon, because we need a lot of science to describe it. And I think it would be really nice to hear more about, say, gravitational waves and,
and how they offer a window
exactly,
into the past.
Exactly. Yeah. That would be very nice. Yeah.
I was gonna add that I really like this explanation, and actually the fact that like black holes are in some ways so simple compared to many other astrophysical events makes them actually so good for like understanding like their progenitors, like things like stars, because when they collide, they provide this gravitational wave signal, and it's actually relatively easy to really obtain precise properties of the black holes from these observations, because black holes are relatively simple compared to any other astrophysical event.
I wanted to ask some questions about gravitational waves. Maybe you guys can, and Floor, that is a specialist.
Can you repeat the question? Because they
we will repeat the question.
Maybe you could try to explain where they arrive in theory, and if they have to be from black holes or conjugations of black holes, and where can we look for them in the universe?
So the question was, can you tell a bit about the theory behind gravitational waves, where they come from, single black holes, sets of black holes, or other objects? Is that right? And where can we look for them?
Yeah, this is a great question. And so the easiest way to think about it is that gravitational waves come from accelerating masses. So if you just have a single black hole, it doesn't necessarily produce gravitational waves. But as soon as you have 2 black holes or 2 masses that are, for instance, orbiting around each other or accelerating through space, But it's also like any two masses, so even two people dancing on Earth produces like gravitational waves. Now, we're often looking at black holes because these are so dense in gravity that just their gravitational waves are so much stronger that we can actually like observe them and detect them. Because these signals are super, super small. You can compare it, like the precision that was needed to detect the first gravitational waves from these black holes that are pretty massive and colliding was the same sensitivity that's needed for like the biggest lake in Portugal. If you were to add like one like bottle of water and then want to know the difference in volume of that lake, like it's super, super precise, like smaller than the size of an atom. And so this is why we often have to rely on these like very extreme events that we can actually detect that produce waves big enough that reach here on Earth and actually produce like a big enough signal. So this is why typically people look at like black holes that are colliding, two neutron stars that are colliding, so also very dense and heavy objects, or these like supermassive black holes that reside in galaxies colliding or interacting with each other.
I have a question. It's not about gravitational waves, but it's also more theoretical. So when we talk about black holes, often we also hear the word singularity when we hear about black holes. But what does it really mean in physical terms, mathematical terms, and does it come into play into your fields of research?
So the question now is about singularities in black holes and what do they mean? So maybe I can take the mathematical singularity. It is true that people typically think about singularities. Typically, if you read a popular science book, you will learn that a black hole is something that has an event horizon. But then you also hear associated to it the notion that it has a singularity at the center. First, I would just want to say that being a black hole, it doesn't mean that you have a singularity. It just means that you have that event horizon, that line that distinguishes the inside from which the future is in the interior or whatever.
Inwards.
Inwards. The future is inwards from the outside, where the future is wherever you want to go. You're not constrained. So that's the feature of a black hole. But then this thing about having a singularity on the inside, I think it's very much up in the air. So it is definitely true, for instance, if you take these curved black holes that we've been talking about, let's think about them, right? Now, let's not for the moment think about astrophysical black holes. So if you take these curved black holes and you look at the case where they're not rotating at all, so they're just, not rotating like this, just standing still, let's say, zero angular momentum, then you will see that it has a singularity in the interior. And what does it mean? Well, it means that if you cross the event horizon, nothing will happen to you. You'll be fine. You won't even notice. It's just that if you try to communicate with people outside, they will never get back to you. But you won't notice that you've crossed the event horizon. But if you go if you continue, okay, and you go towards this singularity, you'll see that then you'll notice something. You'll notice that you're crushed by infinite tidal forces. Mm-hmm. But then if you look at black holes which rotate, suddenly there's something very different that happens. So if you look at exactly this solution, this pure solution that we've been talking about, you won't find a singularity at the center in the same way that you will for the case of no rotation. In fact, what happens is something very strange, that at some point you will cross the boundary of what we can predict will happen to you. And then I don't know what will happen to you. They're infinitely, so somehow there's a boundary. If you think about, well, you can think about these, the Einstein equations, you can think about them as, in some sense, wave equations, which is not surprising because there's gravitational waves. So there's a certain wave-like character. And if you think about waves, for instance, when you drop a pebble in a pond, one thing that you can see about the ripples that you generate is that they propagate at finite speed, right? Like you can see them propagate. So at some point you drop the pebble in the lake, and here, once it has fallen, this part of the lake doesn't know about it yet, right? So it takes some time for that information to propagate there. And the same is true with the Einstein equations, that time is the speed of light somehow. There's a finite time, and the maximum speed is the speed of light. Okay, so what this means is that if I give you an initial configuration, then there's also sort of a finite time. There's a finite time that this information takes to go through. And so there's somehow an edge to what we can predict. Okay, so that's, and if you go to a curved black hole, this is exactly what you'll encounter if you cross the event horizon. You can go until there's the edge of what we can predict, and then I don't know what happens to you. But, so then we can talk about astrophysical black holes. So this is very strange, right? Then we can talk about astrophysical black holes. In astrophysical black holes, we expect that, well, because there's stuff going around in the universe, you can never be at exactly, you can never achieve this exact Kerr solution, because as I said, the Kerr solution is an empty universe that only has that one black hole. So if you now consider a realistic scenario where you don't have an empty universe, there's just one black hole, that means you'll have somehow, you might have something that looks like that Kerr solution, but it will be a little bit different. And what we expect is that the outside of that Kerr solution is still going to very much look like a Kerr solution. And that's why in astrophysics we think about, we think about this as being a Kerr black hole. We think about it as being a Kerr black hole in the outside. But then in the inside, what we believe happens is that that strange picture that I said about you reaching the edge of what we can predict, that it won't happen. What we expect is that in the interior, in these astrophysical black holes, you will encounter some kind of singularity before reaching the edge of what we can predict. So there will not be, you won't cross over into land unknown. There will be some determinism because there will be a singularity. Now, will this singularity crush you? No. It will be a weaker singularity than the kind of singularity that you might encounter in a black hole which is not rotating. This part we know, this is a theorem, but we don't know exactly.
I don't understand that.
You don't understand?
No.
Not being crushed?
No. I think all black holes have a singularity, okay? Either rotating or not rotating. But there is no other way any particle that goes in, for some reason, you would go to the singularity. No, there is no other possibility.
So, but it's just the first part, which is, you said all black holes have a singularity inside. Yes. But there's a problem, say in a rotating black hole, okay? Before reaching the singularity that you have in mind, before reaching it, you will have to cross the edge of what we can predict. We don't know whether this singularity is there. You are correct that there is a way to extend which contains a singularity.
One thing is if you have a particle approaching a rotating black hole,
yes.
In some cases that particle might avoid to get in.
Yes, of course.
That's
No, that's not what I mean. I mean once you are already
inside.
Yes, once you are already inside, you have something which is called the Cauchy horizon, and you will cross the Cauchy horizon before reaching that singularity that you have in mind. You will first cross the Cauchy horizon. Okay? The Cauchy horizon is the edge of what we can predict. So there's infinitely many extensions of the Kerr metric past the Cauchy horizon. One of them has the singularity that you have in mind. This is the ring-like singularity. Yeah. But there's infinitely many others. And
singularities?
that have or don't have singularities, it doesn't matter. And I can't tell you which one you will cross into because it's not predicted from initial data. But it's all saved somehow by this conjecture of Roger.
But if you want to talk about that,
well, I think that let me just add a little bit. So as you can see,
Roger Penrose's name, I think.
Right. So you've all studied electromagnetism to some extent here. So in school, can anyone tell me what's the electric field of a point charge? Yeah, the electric field of a point charge. What's the radial dependence of it? The electric field of a point charge, what's the electric field? Do you know this? Yeah. How does it go? Does it go as, it grows with R, goes as 1 over R squared, 1 over R to the cube? How does it go? Do you remember? Well, the electric field of a point charge goes as 1 over R squared, okay? The electric field. So what happens when you go to R equal to 0, where the charge is? The electric field is 1 over R squared. Well, there's a charge. What happens? There's a constant. When you go to R equal to 0, what happens? It blows up. It's a singularity. So the singularity is because there's a physical quantity, and actually the self-energy, if you calculate the energy, if you integrate all the way until R equals to 0, it diverges. So it's telling you that you cannot trust that formula all the way until r equal to 0. Classical electromagnetism, that is actually describing this electric field, is not valid in terms of going into r equal to 0. Perhaps the charge is not point-like. And actually we know there's an improvement of classical electromagnetism. It's called quantum electrodynamics. And it tells us that a variety of phenomena go around. There's kind of creation of electrons, positrons. There's a kind of virtual particles. So I was trying just to give some more familiar meaning to this apparently mysterious word, singularity, which is sometimes you take a theory and you find it's predicting something that you don't have a physical control over, like the electric field going to infinity. Physical quantities in principle should not be infinity. What does that mean? So in gravity, we find something similar, indeed, inside the black hole. And what that means is under debate, as you can see. I mean, there's a lot of things going on. But the beauty about general relativity is that it hides its own seeds of destruction. This happens behind the horizon. And at least classically, you can make sense of everything just outside the horizon. When you put quantum mechanics into the game, it's something else. So that's why, although you do not understand the interior of the black hole that well, you can actually go and make two black holes go around each other and extract the gravitational waves. And you can actually try to figure out what would be the theoretical image of a black hole to compare it with observations. So that is hidden. It's cloaked by the horizon. Of course, we want to know more, so we want to understand what's inside. But there's a different context in which the singularity is a bit more of a nuisance, which is in cosmology, which is if you go down in the past, and then when the universe was really, really small, you find something which is also a singularity in the same sense. You have that physical quantities are blowing up, and that doesn't allow you to understand what happened according to the physics, the laws of physics, very close to what we call the Big Bang, which is a name for our ignorance at the end of the day. So we would like to know more, and that goes into the direction we would like to put together more of the understanding of our description of the microscopic world, which is quantum mechanics with gravity, and that's an ongoing endeavor, which has been ongoing for a long time, unfortunately. But you see, just as my personal thought on the matter, you see, this probably has to be guided to a large extent by observations. When you study quantum mechanics, you've heard about quantum mechanics, yes? So you know quantum mechanics has all these mysterious things, probabilities and the Heisenberg uncertainty principle and so on, right? Well, if you would try to come up with quantum mechanics without any experimental evidence, so from the atomic spectra or the black body radiation or the photoelectric effect, so you are in the middle of the 19th century, you have nothing, and you give the most clever people in the world the task, find quantum mechanics or find a description, you would fail miserably. You needed some experimental observational guidance in order to come up with a very straight. So perhaps we need some data. And the opportunity right now is that with things like, gravitational waves and things like observations of black holes, these images and other things, perhaps, we will have a glimpse of something that is pointing us in the right direction. And that's really, really exciting. So your kind of lifetime is going to be really, really exciting if you decide to kind of go into this area, because...
Sorry.
I think that Diogo was
Abort
going
your...
to talk.
Sorry.
You should talk now.
Oh.
Continue.
Oh, no, okay. I was just going to... I just want to add something to what you said. You were saying about the black holes and then to the other thing. So the black holes, you were saying that we don't need to know what's inside in order to make all of these statements about what's happening outside. I just want to go back to that point and re-emphasize that point. That's because somehow what happens, because of that light cone, because the future is inwards, what happens inside is completely, what happens inside, it doesn't affect at all what happens outside. But the converse is not true. So if we want to understand what is happening inside, we very much need to know what's happening outside. Things are crossing into the event horizon, right? And that's disturbing what's happening inside. So we really need to figure out the dynamics outside in order to answer these big questions about what's happening inside. Then the second point we were talking about, the cosmological point, I think this might be a good time to ask. I wanted to ask this question. I heard Floor say that if I understood correctly, you study gravitational waves. You're in particular interested in how they tell us something about the past. And I wanted to ask if you can tell us a little bit more about that, because that's a different aspect of black holes that we haven't really discussed. How black holes can be a window into these puzzles about the Big Bang and cosmology in general.
Yeah, of course. Thanks for asking. Yeah, so there's something very special about these black hole collisions that we're now observing, which is that we think they might once upon a time be formed by stars, like these massive stars that are about 100 to 200 times the size of our own sun. And these massive stars, they live very short. They're kind of like rock stars. They have very short and exciting lives. And they actually form a pair of black holes if you start with a pair of stars, maybe in a few million years, which is nothing for astronomical timescales that are often like many, many billions of years, like our sun. However, once you have a black hole pair, it can actually take billions and billions of years before they slowly spiral due to gravitational waves and eventually collide. And so something that's very interesting is that even the black hole collisions that we see today might actually come from stars that were formed billions of years ago, like really high in the redshift, almost as close as like when the first stars in our universe formed. And so this is why this becomes so interesting, because with these black hole collisions, we can actually kind of make a time machine and study stars much earlier in our universe that are not possible to observe in any other way. And the coolest thing, I think, is that currently we have seen about 100 of these black hole collisions through gravitational waves. But in the near future, we're like upgrading these telescopes and these gravitational wave observers so that we actually will see millions of these black hole collisions like per year. And we'll not just see the ones that are nearby us, like colliding nearby our own Milky Way, but we'll actually see every single black hole collision throughout the history of our universe. So that's, I think, what makes me so excited about using them to study these ancient stars that are so important for the evolution of our universe.
Perhaps you could also bring Diogo more into the discussion, and we could tell us a little bit more about what would be the ultimate goal of his project, and also in an ideal world, what would be the results that you would really like to see coming out of it?
So if I may add something to the discussion that we were having, I find it extremely interesting, and I think we have a very varied panel here. So we have pure mathematicians, we have people doing black hole phenomenology, we have people looking at the data, we have people bridging the gap between the two, between what Rita said of astrophysical black holes and mathematical black holes, which, although we make the connection very easily mentally, are actually two completely different things. If you go talk to an astrophysicist and you start talking about singularities, most of them will walk out the door immediately because you cannot observe that in the data. So it's not a question. It's more of a philosophical question, which is extremely interesting. Of course, and I think looking at the theory from the mathematical side, I think gives us a lot of mathematical tools that might be useful for other fields in physics and mathematics. I think that's extremely valuable. And looking at them from the astrophysical side gives us insight into, well, also our history in the universe and how these things come to be. And I think where they actually meet, and that's coming back to what Carlos said of gravitation bringing together not only matter but people. I think that's why black holes are such an interesting thing to study nowadays, because it brings together all of these different sides of physics. And yeah, so to what Floor was saying right now of gravitational waves, of studying these young stars, if I may just add to one of the current problems in astrophysics is what's, for example, called the mass gap, in the sense that we detect small black holes, so things up to 100 mass, 150 solar masses, and we detect huge black holes. So the one at the center of the Milky Way, 1 million solar masses, the one at M87, 1,000 times larger. But it connects with astrophysical questions of how do we go from these small black holes to the huge black holes. And then you start to look at galaxies, for example. And you know that there are correlations between galaxy properties, so the masses of galaxies and the masses of the velocity of stars in these other galaxies, and how that connects to the mass of black holes, for example, and black hole properties. And so I think there are many ways of approaching this, of studying these black holes, and I think it all is in the same bag of understanding how it all connects with the matter that exists. So these are the things that we observe. And so yeah, I'm not sure if Carlos had a specific question for me regarding my research or.
Well, I understood that you were looking at, say, a supermassive black hole like Sagittarius A star in infrared, so in a different wavelength than the ones that are used by DHT. And you told us that you could see a sort of a movie rather than a snapshot of this astrophysical environment kind of evolving and so on. But I was wondering about something more specific about your own project and what are you trying to accomplish, and in an ideal world, what would be the outcome that you'd like to see from it? So, yeah. Yeah.
Okay. So if I can take on that. So as most of I think everyone in the room, I cannot see them, but I think everyone is already. The way to study black holes is through light, and well, gravitational waves as well. But light plays a fundamental role even for the study of gravitational waves. But light is the key to understand them, because they bend light and they move light in ways that we don't experience on a daily basis. Not only by curving the trajectory of these light rays, but also changing, for example, the frequency and the color of this light. And so by studying these things, so for example, one of the things I work on is studying exactly these motions that we see super close to Sagittarius A stars. So we see motions, so we see things going around at around a period of 1 hour, and it's a big question what it is. And so we need to look at it in different ways, in different wavelengths, and not only that, but for example, different polarizations. I think if you have polarized glasses, for example, it would be the equivalence of having your glasses put like this or having your glasses put in the vertical. And when you take a picture of the black hole, or when you do the observation, you see that these polarizations, so the way the light hits your eyes, it changes. So if you look at it, if you look at the black hole with your face like this, or if you look at your face sideways, it changes. And these kind of things gives us information about, for example, the magnetic fields around black holes, which is also an extremely important thing to study, because as Rita said several times, they don't exist in vacuum. So they're always interacting with this matter around them. And how they evolve, it's complicated. So just to give an idea of the current idea, so of the current understanding that we have and what we study, we see this thing moving around, and the idea is that we have the black hole. It has an accretion disk of matter that most likely comes from the wings of stars that are outwards and that blow this matter into the galactic center. And then all this matter spirals inward and creates this accretion disk that interacts strongly with and has its own magnetic field. And in that process, sometimes it lights up. And when it lights up, we see this huge flare from the galactic center that rises and goes away in, again, the time of 1 hour. And the way this light behaves in different wavelengths, so it can be in radio or in the infrared, gives us insight into the geometry of the space-time around this black hole. And I'm calling it a black hole, but one of the interesting things that one can do is ask if it actually is a black hole. It explains to this day very well everything that we see. That's astonishing. But there's some room for other things. So there's room for alternate theories of gravity. There's room for other possibilities that might also solve, for example, dark matter. And so studying this emission from these black holes can be the key to give new insight into, well, our understanding of gravity and general relativity as a theory. So yeah, I think that's I think I spoke for too long.
No, that's very good.
We got here a question from the audience at YouTube. Maybe you can then repeat it so that the audience online the panel online can also hear it. So, in relation to Hawking radiation, what happens to the particle that falls inside? Is the information somehow lost, destroyed, or does it survive in any other way?
So the question was in relation to Hawking radiation, what happens to the particle that falls inside, and is information lost, destroyed, or preserved in any other way? That's the question. Okay. So I repeated the question. You want to tackle it?
Well, you are thinking about the particle that, well, is a particle that gets inside. Probably is going to go to the singularity, and that is it. The other one stays outside. That's all we can say about that. So,
I think in this scenario, the two particles are entangled in some way, so that is that right? And so the information is somehow preserved. The information for the particles going in is somehow preserved because they are entangled. Is that right in your explanation of?
I think so.
So perhaps I can say something which is, I think the audience doesn't probably know this so-called information paradox, which is something that came about in the 1970s. So before, there was only a classical description in which black holes are these one-way, these are trapping regions of space-time. There's this virtual boundary, the event horizon, which is a one-way surface and things can only go in. Then with the addition of quantum effects, apparently black holes could evaporate by emitting this Hawking radiation. And in the original Hawking computation, the Hawking radiation had a property which is that it is thermal. Thermal radiation is a sort of thing that doesn't have, its information is somehow scrambled. You see, let me tell you that we believe, and quantum mechanics, which is another pillar of our understanding of fundamental physics, establishes that probability, information is conserved. And this comes by the name of unitarity. Information is preserved. So happens that in this process, if you throw things into a black hole, the black hole grows. Everything is just transformed somehow into its mass and angular momentum. That's all there is. And then when it evaporates, it actually leaves behind this thermal radiation, which doesn't have a lot of information. And if this would be extrapolated all the way until the black hole would evaporate, then whatever you threw into the black hole would kind of come out, be transformed into this thermal radiation. In quantum mechanics, this is a non-unitary evolution. It means information is not preserved. So Hawking, when he kind of observed this, he said, you know, we'll have to change quantum mechanics, because he was kind of into gravity, so he thought, no, black holes are telling us that we have to change quantum mechanics. Unitarity is a kind of fundamental principle of quantum mechanics, this conservation of information. So this was a debate for a long time. Is it really so? I mean, is the information encoded somehow in a subtle way in this radiation that's coming out, the Hawking radiation? So I would say that, you know, this is a kind of a complicated thing, but I can tell you that I was in 2004, there was a famous conference, the GR conference. It's a conference organized every 3 years, and this one was in Dublin. And at the time, there were some developments about this question using what Rita was saying, this ADS-CFT. So it's a kind of a relation between some particle physics theories and some gravitational space-times. You can get information from one from the other in kind of non-trivial regimes. And using that, Hawking convinced himself that indeed there was a way in which information was actually preserved. So there was a famous bet that he had actually put out with John Preskill, he's a physicist, and he conceded the bet, so that indeed information was preserved in some way. No one really understood very well because he had his own little model, and it was a very awkward situation in which he put out his PhD student to explain to everyone how that was working out, and the PhD student was really, really in trouble. Anyway, so I think this is under debate to some extent. All quantum aspects about black holes are really under debate, I would say. There are some very clever ideas, some very important ideas, but it's still something under debate. So, what happens if the black hole evaporates? So is there a remnant? How is information then coming out? What are the kind of properties of this Hawking radiation? So this is a little bit, I would say, under debate, but that's my opinion.
You have to wait a very long time, right?
You have to wait a very long time, which is also important.
Exactly. Hawking radiation takes so long.
Right. But it depends on the size of it. So black holes are very strange systems thermodynamically because they have a negative specificity that I'll explain. So their temperature goes as the inverse of their mass to some power. So it means that for a very large black hole, like the ones that came out from as the endpoint of the evolution of a star, so their temperature is tiny, 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 much lower than the CMB temperature. So if this is to kind of radiate away until it kind of slowly grows, slowly decreases, it will take more than the lifetime of the universe, but much, much more. But if tiny black holes, by some other mechanism, were created, these are much hotter. They have larger temperature, and the larger the temperature, the faster they emit. So there's been some ideas that there could have been black holes created in the early universe by some mechanism. They could even be part of dark matter. And these, in some regime, they could evaporate within the lifetime of the universe. So those would be, and there was actually a famous paper by Hawking called the black hole explosion. So he was conjecturing that we should see explosions in the sky corresponding to, the kind of the endpoint of what was going on with these black holes. We haven't seen any. But all of this is very exciting. All of these kind of possibilities when you put together quantum mechanics and GR. But for once, and this is clearly not a unanimous consensual opinion, I think maybe the time for some of these questions, or at least the answers to them, maybe it hasn't come yet, because it needs data. In the same way that I was trying to tell you, try to come up with what is the atom in 1850 without any experimental data, and you just fail. We can use mathematics and our physical intuition and our previous models as a guiding principle. Is that enough, though? For once, I have a lot of doubts, but take that as an opinion and not more than that.
I think there was another question.
Yeah.
I was going to ask about the possibility of wormholes.
Well, Paulo has worked on wormholes, and I guess maybe he wants to.
On what?
Wormholes.
Wormholes. Well, what's your question?
If they match with the theories that we already have, and what are the flaws with this theory that they haven't been proved to be real yet, and is the thing that we all agree on?
Just to repeat the question is about wormholes, if they are somehow in agreement with the theories that we have, and if we've tested them in some way.
I don't know what. Sorry, I have a problem with this situation. Besides having my apparatus to be listening, I have very difficulty in here with many people speaking and to understanding what you are saying. That's a bit of a problem. But just tell me.
To talk a little bit about wormholes, how do they appear, and if they are somehow realistic, I guess, or perhaps talk a little bit about this sort of space-times.
about space-times, different space-times.
Wormholes, yes. Wormholes, yeah.
Let me see if I can remember anything about that.
Well, maybe I can take a bit on the question from a more practical view, and this is connected more with the Occam's razor. I don't know if in the room people know what the Occam's razor is. I cannot see the people in the room, but essentially, if you have two explanations, tell me.
Oh, sorry. Can you see me?
Oh, I thought it was from you, Rita.
No,
sorry.
No, sorry. It's just that our tablet is almost dead, and I was trying to.
We need to charge it.
Yes.
We have to charge it.
Battery is gone. Almost gone. Not yet, but it's.
You can go ahead.
Yeah, Diogo, go ahead.
Yeah, no, but so essentially what I was saying of what the Occam razor's principle is, if you have two explanations for something in physics, usually you go for the simplest one. And that's why usually we go for black holes. That doesn't mean that we cannot take wormholes. And for example, with the data we have, we can start to do some tests. But more often than not, either the black hole explains it better, or, and this is purely from a data-driven approach, so looking at the data, the black hole itself explains the data, and the wormhole would, for example, have to have a super small throat. So a wormhole essentially connects two regions of space-time through essentially a space-time tunnel. And so the larger this channel, the more different it is from a black hole. So to make a difference, you would have to have a big wormhole to go through, or and so usually you cannot either a black hole works very well, or you would need a super tiny passage in a wormhole. Of course that, and I think from the theory side, maybe someone can correct me, but usually for wormholes to form, you need some sort of exotic type of matter, or you need some extremely unfavorable conditions in the space-time per se to form this kind of objects.
You said there is needed some sort of
exotic matter.
Exotic matter. I don't think so. Why exotic matter is necessary, is needed for that? So the black hole, the wormhole. No, I don't think so. I don't remember that. Anyone know anything about
Yeah, I think you need to, from throat conditions, to violate some energy condition, perhaps the weak. Yeah, so, but I just don't agree, well, not agree. I think you phrased it like in order for the wormhole to form. I would say for the wormhole to exist, because I would put two different things here. So one of the issues about these sort of geometries is how do you form them? You see, black holes being very exotic, we have mechanisms to form them, which have been tested, at least, in many theoretical computational ways, and we believe the ingredients are present in the universe. Gravitational collapse. There are stars which are sufficiently massive, they burn their nuclear fuel, and at some point that they cannot withstand their own weight, they collapse. Some of them form neutron stars, but if this kind of nucleus, the core, is sufficiently heavy, there is nothing that we know, no known force, no known interaction that can prevent the collapse. And therefore, you would form some kind of gravitational collapse that forms a black hole. For other so-called exotic objects, and some of them are compact, like wormholes, we can find them somehow as, solutions to our field equations, but then again, anything is a kind of solution to the field equations if you put what is necessary there. And hence the question about what is the sort of matter that supports. And for wormholes, at least in general relativity, if you go to modified gravity, that's not the case. But then there are other issues. You would need some matter that we don't really know, that's normally described as violating some of the important energy conditions, like that the energy is positive, or that perturbations in that type of matter propagate the speed that's smaller than the speed of light, or that they produce, attractive gravity. Although that case is particular because in the universe as a whole, we seem to need that in order to describe inflation. But that's another matter. If you talk about objects like wormholes, which are very interesting from the theoretical viewpoint, and actually, they have a long story. We could go into that, and they were somehow popularized also by a very famous relativist, Kip Thorne, that wrote an influential paper, actually several, about this, and gave rise, if you've seen this movie Contact, there's a wormhole that is able to, and Kip Thorne was in touch with Carl Sagan in order to find a way to kind of minimize traveling to kind of very far away distances, and they thought the wormhole would be a possibility. And so they kind of connect to science fiction, but realistically speaking, we don't know of any way to create what's a wormhole, because wormhole has a non-trivial topology. What that means seems complicated, but you see, if you have a sheet of paper, you bend it. And if you want to go from this point to that point, you have to go all the way around. But then you can actually kind of create a little, you deform and make a hole, and you connect also the two pieces, the upper one and the lower one. This changes the topology because now it's a multi-connected space, and it has different topological properties. So topology is a property of mathematics that's related to, global properties, say, of a manifold in this case. And then you see, this doesn't have the same topology of the original sheet of paper and flat space. So in order to create something like that, in general relativity, you need to change topology. And in classical general relativity, there are theorems that tell us that in order to achieve that, you create singularities. So we go into a realm where we don't trust general relativity as the full description. So people typically wave their hands and say, but quantum effects. And quantum effects would come to the rescue, and that is how you would be able to create these things. But it's an idea which is not really materialized. And so I think that it's a very, like many other classes of these, hypothetical. Let me just conclude by saying this. Black holes were once, and for many years actually, not understood theoretically and thought as extremely exotic objects themselves. The reason why we are now talking about black holes is because they impose themselves, the need of them to explain the data. So history teaches us to be open-minded. Something that was once considered to be extremely exotic now became a sort of fundamental ingredient of the physical universe, in order not only to explain, kind of what's going on in the center of galaxies, but there's a very interesting, say, correlation between the overall mass of galaxies and the mass of the central black hole, although they are kind of orders of magnitude apart. So they might play a very important role in the growth of structures and so on. And so I think we should be open-minded and say, okay, we don't have the need or any evidence of these sort of objects, like wormholes. They are a theoretical possibility that defies a lot of our kind of beliefs, and they don't have a kind of formation mechanism. When they form, they are, many of them, unstable. I'm not sure how general the statement is, actually. And so, can they play a role in the macroscopic universe? It's not clear. We need them. So, Diogo was talking about Occam's razor, and that's kind of going that direction, which is we don't need that sort of far-fetched object in order to explain what we see. But we should leave an open mind, because, we get surprises every now and then.
Thank you.
Thank you. So,
Also, unfortunately, we are running out of time, so
right.
we should accept one more question. Okay.
There's two.
You can. You have to play game.
I have a question related to the origin of supermassive black holes, because apparently they are too big for the universe itself.
So the question is about supermassive black holes, and it was phrased there as apparently they are too big for, and you said the age of the universe, is that what you said? Yes. So I don't know, maybe Flora, would you, I don't know if this goes, oh, she's gone, okay, I see. She would come to the rescue now.
No, but so I may reply to the question. So the thing I said earlier is we know how black holes form, at least so we know the black holes that form from, for example, the collapse of stars at the end of their lives. And usually these are not extremely massive compared to what we see at the center of galaxies all across the universe. And so it's an open debate of how can we get black holes that big, given that we know the age of the universe. Because for that, you would need to get either more matter falling to the center of these galaxies, and we don't see that in galaxies, or you would need to have galaxies merging with each other much more often than what we actually observe. And so how you can go from these small black holes to millions of solar masses black holes, it's not a trivial question. And it's an open question right now.
In some galaxies, this is more a cosmological way talking about black holes. But in some galaxies, the amount of star formation is decreasing, and eventually it stops forming stars. But some researchers found out, and they realized that in these galaxies that don't form stars anymore, the central supermassive black hole it continues to grow and to get heavier and heavier. Can this explain in some way dark energy and therefore the expansion of the universe, or it just doesn't have an explanation yet?
Well, I personally, I can say my 2 cents, but I don't know the concrete case that you're talking about. First of all, I would say that, well, there was a recent speculation about some relation between black holes and dark energy. But I think the essential, many people would think that dark energy, which was, again, a sort of name for our ignorance about what is the engine that is accelerating the universe at the moment, and that people can put in the Einstein equations as the cosmological constant, I think that you mentioned already, that, this works at the scale, which is the kind of Hubble scale. It's huge. And you're talking about something which is more astrophysical. So if you meant dark matter, I would conceive more easily that there could be a relation, some sort of dark matter is being, kind of absorbed into this black hole, and maybe that is explaining its growth, or there could be millions of other explanations. But to relate such a small astrophysical observation, even if you think that the supermassive black hole at the center of the galaxy is big, it's tiny as compared to the cosmological scale. So, you see, we think about dark energy as something that first, it's not clear if it clusters, if it forms structure. It seems to be some sort of fluid that is dominating and leading this accelerated expansion of the universe. But unlike dark matter, it's not clear if it forms structure, you see? And what you're talking about is something that's being absorbed by the black hole, and therefore, it's forming structure. So a relation with some sort of dark matter models, because we believe that galaxies have halos of dark matter, and this could be accreted by a central black hole, and there could be different dark matter distributions, and some of it could be absorbed, is conceivable. But dark energy, I find it more difficult to see the relation. But maybe it's my ignorance, and I don't know the particular case you're talking about, so that's what I can say.
I think your answer just highlights the glaring thing here in this panel, which is there's a lot of things that we don't know.
Absolutely.
And that's why we need all of you.
That's right.
So, you can.
Yeah. Do you think that micro black holes can be possible? They can
By micro, you mean what scale?
For example, less than a stellar mass.
Well, there's been a discussion about this. So first of all, one of the beautiful things about these theoretical solutions is that mass is a free parameter, and it could run, all possible scales within the regime of validity of the theory. So apart from, we know that very, very microscopic scales, you probably expect that some sort of quantum gravity is necessary, then this solution exists at whatever scale you want. Now, the question is, do you have any mechanism to form black holes in the particular scale that you're talking about? So, for instance, we know that stars exist because we see them. According to our best understanding of nuclear physics, we believe some of them will collapse and lead to black holes. And from this sort of mechanism, you'd expect black holes forming from a few solar masses. The number is a bit debatable here, but we have evidence for 5 solar masses, say, until perhaps more than 100. There's a little bit of a gap. There's something called the peristability supernova gap. But anyway, so you would expect this type of things. We also have evidence for a different range of black holes, which are the supermassive ones. And the mechanism to form those, especially in the early universe, because we have evidence for that, is still under debate. But, I mean, there's various theories, although this is a question, because there's a limit to the accretion rate at which black holes can grow. You see, it's very simple to understand, because if they are kind of, absorbing a lot, this is matter typically ionized, then as it's falling in, then it's emitting radiation, so there's radiation pressure. So at some point, there's so much radiation pressure that it will prevent more matter from coming in. It's called the Eddington accretion rate limit. And therefore, you cannot just grow as fast as you'd like black holes. So, but now, there's a lot of speculation about other scales. For instance, a few years ago, there was a theory of large extra dimensions that said, well, you collide at the LHC when they improved the luminosity and energy scale. They got to about 14 TeV, center of mass energy. And the idea is that because there could be extra dimensions, then in these collisions you could create microscopic black holes. And some people were worrying that they could grow and absorb, kind of engulf CERN and then the whole world, and it would be the end of the world. It didn't happen. No one saw any evidence for black holes. In the early universe, there could be indeed, and there are people that study this formation of primordial black holes, which would have smaller scales. I don't know precisely the numbers, but if you want to look it up, if it matches what you're saying. So, yeah, there could be other regimes of black holes mass that we haven't seen direct evidence about, but you need to come up with some possible formation mechanism, and of course then some evidence for them. But in terms of the theoretical solution, yeah, anything goes. That's kind of very interesting. So there is no, for stars, there's kind of limits to the mass they can have, but not for black holes.
So I think we can end this roundtable. I enjoyed a lot, and in behalf of everyone, I want to thank Rita, Paulo, Carlos, and Diogo and Floor, that is not here, for your time and for your detailed explanations. Thank you so much.
Thank you. Thank you for the invitation. Thank you. All of you for the questions. There were a lot of interesting questions that I don't know the answer to, and I guess we all are kind of puzzled about them, but very nice questions.
I don't know what to say. So right now we have a coffee break.
Okay. Okay, enjoy. Yeah, that would be nice.